Sea levels are increasing, Arctic ice is melting, Greenland is bursting with flowers, and glaciers are retreating. Stop the warming trend, or the planet will perish. This is essentially the constant message we've been exposed to over the course of many years. Why shouldn't we take it seriously when everyone keeps saying it? Few people still insist that the anthropogenic cause of global warming can only be inferred from intricate computer programs called general circulation models, which are still only unproven conjecture. Contrarily, the existence of natural climate variability that computer models are unable to replicate has been noted more and more in scientific literature. A sizable amount of the observed global warming since 1850 can be attributed to this natural variability. Therefore, the anthropogenic contribution to the observed climate change over the past century is unjustifiably overstated, and the dire predictions are unfounded. Climate is the most complex system on our planet, and as such, it necessitates proper and well-thought-out responses. A small group of climate change skeptics contend that climate simulation models fail to accurately simulate the observed natural climate variability, particularly when it comes to constructing the warm periods of the past 10,000 years. These periods, which include the well-known medieval warm period, the Roman warm period, and generally prolonged warm periods during the Holocene optimum, occurred around every 1,000 years. Despite having lower CO2 concentrations than now, these earlier times were much warmer than the present and are associated with millennia-long cycles of solar activity. So who should we pay attention to? Let's talk about it. First and foremost, those who believe that there is an impending climate catastrophe should limit their warnings to the potential existence of the human race, rather than the end of the world and all biological life. Our planet has experienced shifts of such scale during its roughly 4.5 billion year history that the current one, assuming it is real, resembles the bite of a minuscule fly. No, human activity cannot cause the Earth to become sick or die. Let's not deceive ourselves about this. Even if we like to think of ourselves as strong and unbeatable, the truth is that we are completely at the mercy of the natural world, where our existence means nothing. Let's think about the wonderful evolution of the dinosaurs, who lived for over 180 million years until being obliterated by the collision of an asteroid with a modest 10-kilometer diameter. The consequences of a typical explosion of a big star close to our Sun would be catastrophic. The Earth is neither sick nor dying. Rather, it is continuing its extraordinary adventurous existence, never exactly replicating itself, and prepared to support life once more, as it has done on numerous occasions. In actuality, cycles of significant changes in the average global temperature have been observed in Earth's recent past. Glaciations, which appear to have occurred roughly every 100,000 years, are the most obvious evidence. Significant short-term fluctuations have lasted between glaciations and even during them, capable of completely changing the environment in which life might survive. In essence, glaciations impacted Europe up until roughly 10,000 years ago, at intervals of several thousand years within the larger 100,000-year cycle. Cycles, or repeating sets of occurrences, are the very foundation of our existence. In the universe and in our world, cycles come in huge variety. Some of these, such as the seasonal changes, yearly animal migrations, or the circadian rhythms that control our sleep patterns, are natural. Others, like crop planting and harvesting, musical beats, or business cycles, are man-made. What could have caused Earth's glaciations and thawing to alternate? Milankovitch, a Serbian mathematician, contributed to the discovery of the solution in the early 20th century. Through his studies, he became convinced that the Sun, Earth, and other planets are not ideal billiard balls traveling in continuous identical orbits and rotating in the same way, which might be used to characterize the entire cycle of major glaciations over the previous millions of years. In the universe, everything is always changing and becoming something new. More specifically, the Earth's orbit path has an eccentricity of about 0.0167 and is currently almost circular. That infers that there are about 5 million kilometers between aphelion and perihelion. Additionally, due to gravitational interactions with other planets, the eccentricity of the Earth's orbit can change up to a value of 0.058 during the course of a cycle of around 92,000 years, resulting in an aphelion and a perihelion distance variation that can reach 17 million kilometers. the tilt of the Earth's rotation axis to the plane of the ecliptic, which is currently 23.4 degrees and oscillates from 22.5 to 24.5 degrees in around 41,000 years, is another notable change. The third significant fluctuation is related to the axis orientation and is brought on by the equinox precession event. Due to this, the equinox line gradually shifts over time, circling 360 degrees in around 25,800 years. As a result, Earth adopts opposite inclinations with respect to the direction of fixed stars roughly every 12,900 years. These astronomical cycles affect how much solar energy reaches Earth at certain latitudes and seasons. For instance, a more inclined axis results in more pronounced temperature changes across seasons, whereas a less inclined axis produces more consistent seasons. The total solar energy that Earth receives over the course of a year varies as a result of orbital eccentricity. These cycles' combined influence have the potential to significantly alter Earth's climate. Warmer periods, known as interglacial periods, can occur when variations synchronize so that solar energy is focused in the northern hemisphere during the summer months. Sea levels rise and glaciers retreat during these periods. On the other hand, glacial periods, which are marked by widespread ice cover and lower sea levels, can occur when fluctuations result in diminished solar energy in the northern areas. It is vital to realize that seemingly insignificant temperature differences control the transition between glacial and interglacial periods in this regard. Remember that a glacial period's average temperature is only 4 to 6 degrees Celsius lower than an interglacial period's average temperature. The impacts that can be seen, however, are striking. Life on Earth becomes fairly hostile during ice ages. Much of North America and Europe, as well as areas of Asia and South America, are covered by thick ice sheets similar to those that currently exist at the poles. Sea levels drastically decline when glaciers hold more and more water. For instance, it is estimated that the average sea level fell by around 120 meters during the last glacial epoch, converting the Baltic Sea into a lake and changing the United Kingdom into a peninsular home to mammoths and enormous hairy rhinoceroses. On the other hand, during interglacial times, like the current one, the climate gets noticeably milder. Sea levels increase as northern Europe largely emerges from the ice. Analysis of climate data and geological evidence has shown the relationship between Milankovitch Cycles and Earth's climate. Climate change over millennia, which can be correlated to astronomical cycles, is well documented in ice layers, marine sediments, and carbonate deposits in caves. Thus, Milankovich's idea has developed into the strongest defense against the thesis that human activity is to blame for the Earth's warming over the previous 2 decades. It must be acknowledged that this theory of cycles by the Serbian mathematician has only been somewhat successful in explaining long-term climate changes, those caused by significant glaciations interspersed by periods of thousands of years. As a result, those who believe in man-made global warming and who promote this theory have little trouble refuting the claims made by climate change skeptics. Milankovitch Cycles cannot help in the search for a theory to replace man-made global warming. But is it really true that there haven't been instances of climate change lasting several decades? If that weren't the case, one of the fundamental tenets of the warming driven by human activity theory would fall apart. What climate changes with the existence of Neolithic and medieval humans, of course? And we didn't pick these 2 eras of history at random. Keep in mind the 5,000-year-old Iceman, Ötzi as his discoverers dubbed him, whose mummified bones were discovered in 1991 at a height of about 3,200 meters amidst the thawing ice of the Italian Alps. What role did Ötzi play? A hunter? An overseer? It's difficult to say. Frankly, it's anybody's guess. But he most definitely wasn't a mountaineer ascending to those heights. In fact, there's something peculiar about this story. Just a few decades later, a Neolithic villager was already at 3,200 meters above sea level and being pursued by someone who managed to kill him with an arrow in the back. 10,000 years ago, the Alps were still covered in ice due to a glacier. In any case, it's hard for us to conceive that Ötzi perished in the snow and ice. A quick warming period that had already cleared those altitudes of snow is far more probable to have occurred when he closed his eyes for good. This indicates that a significant thaw had already taken place by 3000 BC, enabling humans to travel easily from Austria to Italy at extremely high altitudes. a thaw that was undoubtedly larger than the one we are seeing right now, and it happened extremely quickly. How do we account for the sudden drop in temperature that must have followed, leaving Earth's remains covered in ice up to the present day? This indicates that there is no truth in that there are no short-term climate fluctuations. They literally abound throughout Earth's history, all occurring spontaneously and without interference from or blame towards humans. Even in times more recent than our own, similar occurrences have occurred repeatedly. The unexpected mild era between 1000 and 1300 that permitted the Viking Eric the Red to occupy Greenland and later discover America comes to mind. Or the Maunder Minimum, a period of extreme cold that affected the whole northern hemisphere from 1645 to 1715. Although few people are aware, there was discussion of an unbearably cold climate approach in the 1970s, with plans to cover the North Pole in coal dust. Currently, there is a phase of gradual warming. The catastrophists, who have gained the support of the media and the political establishment, appear to be more and more convinced that a form of Armageddon is imminent as a result of human activity. However, just as it did during the Maunder Minimum, which brought nearly 70 years of extreme cold between the 17th and 18th century, the Sun has undoubtedly been experiencing low levels of sunspot activity for some time now, almost completely disappearing. In fact, while some scientists contend that there is little data to support such a claim, others predict that this could be the start of a recurring solar occurrence known as the Great Minimum. A grand minimum affects the Sun's magnetism, the frequency of sunspots, and the amount of UV radiation that reaches Earth. A grand minimum, like Maunder's minimum, can continue for decades or even centuries. Even though Al Gore's heirs assert that they are correct a priori, the confusion is considerable. To summarize and further our points, the situation between the two factions is roughly thus as follows. Short-term climate variations are not adequately explained by Milankovich's astronomical cycles, but long-term ones are. Fossil fuel is to blame for the rapid changes we're currently experiencing, according to proponents of global warming. On the other hand, climate change deniers provide evidence of similarly quick climate shifts that happened during times when human activity couldn't have affected the environment. So, how does this resolve this? Do you think there's something we missed? Maybe volcanoes with their enormous and unstoppable carbon dioxide emissions? That may be the cause, but catastrophists ignore this and assert, incorrectly but we'll give them the benefit of the doubt, that recent eruptions haven't been very volatile. The continental drift can be yet another significant cause that is overlooked. There is no question that the joining or splitting of continental masses can have a significant effect on the climate, but these changes only take place over tens of millions of years. Is there truly nothing more to take into account? Well, it sounds almost ludicrous to say so, but not a single mention of the Sun, the only genuine source of energy in the entire solar system, has been made in any of this discussion. Catastrophists have thought about it and used complicated mathematical models to predict it, but they have understated its significance to a meager 7.5%, seeking to find other explanations for the brief warm and cold spells that have occurred over the previous 2,000 years. The Milankovitch Cycles, however, which regrettably only suit long-term oscillations and do not account for the changes in the Sun's luminosity, have been overly emphasized by climate change doubters. The Sun, in fact, doesn't always shine at the same brightness. Rather, over the course of an 11-year cycle, its brightness dims or brightens by 0.1%. The Sun's activity and appearance fluctuate significantly throughout this time. The amount of matter the Sun discharges into space, the size and frequency of sunspots, and the amount of solar flares all change with variations in solar radiation levels. These modifications have a variety of impacts on the surface of the Earth, the atmosphere, and space. The scientific community lacked concrete proof of a link between solar variability and climate changes up until this point. The transition from El Niño to La Niña, which is the atmospheric shift from warming, El Niño, to cooling, La Niña, of the waters in the central eastern Pacific Ocean, is one of the periodic meteorological phenomena that occur on Earth. A recent study from the National Center of Atmospheric Research, however, demonstrates, for the first time, a correlation between the end of solar cycles and this phenomenon. As a result, the study implies that solar variability may act as a controlling factor in changes in the Earth's atmosphere. This link between solar cycles and ocean currents may also account for the recent high in global warming, absolving anthropogenic action at least in part. But the conflict goes on. Unfortunately, we don't know who the adversary is in this war. With such vast interests at stake, has science been put up for sale? There were once fishermen who spent their entire lives on the waves, catching fish and watching the rhythms of the sea, amid the wide expanse of the Pacific Ocean. One day, they became aware of something out of the ordinary. The water was warmer than usual, and odd things were occurring in the currents. They had never seen anything like this before. They started to see a trend when they discussed their observations with others. Every year around Christmas, this strange occurrence would take place. They referred to it as El Niño, which is Spanish for little boy or Christ child. Since it provided warmth to the chilly waters during the winter, they thought this phenomenon was a gift from God. El Niño was part of a bigger cycle of marine and atmospheric changes that had a significant impact on weather patterns all around the world as scientists started to investigate this phenomenon over time. The World Meteorological Organization predicted 2 weeks ago that El Niño and climate change will result in very severe global warming over the next 5 years. Although it's still not definite, it is now more likely than ever that El Niño and heat-trapping greenhouse gases will cause the Earth to warm to record highs within the next 5 years. It's important that we should be ready. It all began with anchovies. Anchovies are in the ocean before they end up on our pizza or in a tin container with a rollaway lid. In the 1960s, bright Pennsylvanian boats used to return to shore every day, laden with thousands of anchovies. This was a blessing for those who had difficulty farming the land due to the arid environment near Peru and Ecuador's coasts. They relied heavily on those anchovies as a source of food and revenue. But in 1972, everyone was dismayed when the fishermen brought their empty nets back. The seabirds, which typically dined on the anchovies, were going hungry and dying. The fishermen observed an odd thing. There were no anchovies despite the water being warmer than usual and the appearance of other fish. The air was humid rather than dry, and the skies were gloomy and cloudy. The locals there gave this occurrence, which would reoccur every few years, a name: El Niño. Today we are aware that El Niño is a crucial component of the ENSO, or El Niño Southern Oscillation weather phenomenon, and it impacts the entire planet, not just the fish in Peru. Knowing the causes of the anchovy deaths will help us better grasp what El Niño is and how it affects the planet. Consider yourself a tiny anchovy swimming in the ocean on the Peruvian coast. Because the water is nutrient-rich and chilly, life is good. This is due to a mechanism known as upwelling, which functions as a kind of elevator for water from the ocean's depths. As you can see, winds from the north drive the surface water away from the coast along South America's west coast. This makes room for the deep water's nutrient-rich surface to rise up and feed the hungry phytoplankton. Additionally, zooplankton can be found anywhere phytoplankton is present, and anchovies can eat zooplankton. But occasionally, something called El Niño occurs. This is similar to an ocean temper tantrum brought on by alterations in the wind patterns. El Niño causes upwelling to slow down, which causes the anchovies to become perplexed, like lost fish in an unsure sea. Fishermen attempt to catch them in the customary locations, but no fish are present. This is bad news for us humans who appreciate a delicious anchovy pizza or Caesar salad because it implies there will be less fish available for consumption. It's crucial to comprehend why anchovies disappear during El Niño, since it sheds light on how our world functions in general. Small adjustments can have large effects elsewhere in the world, just like a small shift in the wind can have an impact on the ocean. It's similar to the game of Jenga, in that one brick removed can cause the entire tower to collapse. So let's be aware of what we can do and how it affects the environment. It is easy to draw conclusions about what El Niño actually is. It is an oscillation of the ocean atmosphere system in the tropical Pacific, having important consequences for weather around the globe. The equatorial Pacific's exceptionally warm ocean temperatures are what define this phenomenon. As shown in Australia, the warming of the ocean can result in deadly bushfires as well as disastrous floods. El Niño is extensively watched since it is crucial for the forecasting of sudden changes in the climate. Weak El Niño conditions and cooler than average water temperatures in the eastern Indian Ocean led to bushfires in Australia during the Black Summer of 2019 to 2020. These circumstances, which frequently but not always coincide with El Niño, encourage drier weather in the southern and eastern regions of the nation. Having said that, the World Meteorological Organization, WMO, just issued a bold and alarming statement regarding the future of our planet. Within the next 5 years, it's likely that El Niño and human-caused climate change will cause global temperatures to reach record highs. Despite the fact that El Niño is a natural occurrence, it is predicted to cause global temperatures to rise in the upcoming months, with uncertain effects on the environment, water management, food safety, and health. The WMO Secretary General, Petteri Talas, says we need to get ready for the effects of this hazardous combination. Furthermore, over the next 5 prolonged Northern Hemisphere winters, Arctic warming is expected to be 3 times greater than the estimated global anomaly compared to the average of the years of 1991 to 2020. The report also predicts a change in precipitation patterns, with more rain falling in certain places and less falling in others. Higher ocean acidity levels, melting glaciers and sea ice, rising sea levels, and more extreme weather patterns are some of the effects of human-induced greenhouse gases. The Paris Agreement placed a strong emphasis on the need for all countries to considerably decrease their greenhouse gas emissions in order to keep global temperatures from exceeding 2 degrees Celsius, with additional measures to keep it below 1.5 degrees Celsius. If global warming exceeds 1.5 degrees Celsius, the Intergovernmental Panel on Climate Change warns climate-related dangers would increase, necessitating immediate action to lessen these negative effects. To guarantee a sustainable future for our world, we must give climate action top priority. It's not all bad news, however. Although El Niño poses a great threat, he is not the only player in the game. The equatorial Pacific experiences extremely chilly ocean temperatures during La Niña, which also exists. La Niña has the opposite impact of El Niño and can boost rainfall in areas that are prone to dryness. El Niño may inflict some harm, but it's not all terrible news. We can prepare for its effects and foresee its occurrence. In a similar vein, El Niño alleviates drought conditions and can provide populations impacted by El Niño with a much-needed break. Although we should approach these meteorological events with respect and prudence, we shouldn't overreact. One must first look closely at the typical state of the Pacific Ocean affected by ENSO in order to fully understand the cause of El Niño. The trade wind system in this area, which is in charge of the dominant winds, is very important in the development of El Niño. The doldrums are a region of low pressure close to the equator. The horse latitudes, in contrast, are the names given to the main high-pressure systems that can be found 30 degrees north and south of the equator. The Western Pacific's tropic zones are warmed unevenly by the sun, which causes the air to rise into the atmosphere. When this hot air reaches the equator on its journey to the doldrums, the Coriolis effect causes it to be redirected westward. The Coriolis force is a second acceleration that affects how objects move in a rotating system, such as Earth. This is crucial in figuring out which way the trade winds will blow. The northeast and southeast trade winds, which bear the names of their points of origin, are created as a result of the Coriolis effect. The typical trade wind system, which pushes air westward over the Pacific equator, is formed when these winds combine. Additionally, these winds produce gyres, which are huge ocean currents that move surface water in a westward direction and are sustained by the prevailing winds. The water depths change as a result of this. Upwelling is the process of cooler subsurface water replacing warmer subsurface water as it travels west. In the Western Pacific, where warm surface water has accumulated into a warm pool, the sea level is typically half a meter lower than in its Eastern Pacific at the equator. Due to the upwelling of these cooler surface waters, the sea temperatures in the west are frequently 8 degrees Celsius higher than those in the east towards South America. Due to the moisture in the winds as they travel over the Pacific, the dominant winds also contribute to heavy rainfalls over Southeast Asia and Indonesia. This entire system changes during El Niño, having an effect on the ecosystem on a large scale. Here is a helpful overview if you're curious about how El Niño may impact your region. El Niño rules over the enormous expanse of South America, tossing caution to the wind and upsetting the continent's weather patterns. The normally barren and lonely western coast of South America experiences exceptional excessive rainfall, which causes floods of devastating proportions. This phenomenon is brought on by the warming of the Pacific Ocean's subsurface waters, which cause the ocean's oxygen content to drop. Fish become scarce as a result, which has negative economic effects, especially in Peru and Ecuador. During the summer, the eastern part of South America, which includes nations like Brazil and Argentina, experiences an increase in atmospheric humidity. On the other hand, the winters are moderate and don't typically bring heavy snowfall. Dependent on latitude, El Niño behaves differently throughout North America. On occasion, intense downpours in the Caribbean and the southern United States completely wreak havoc. The warming of the surface water causes milder winters and springs with greater temperatures as one proceeds further north, from Oregon to Alaska. Moving on, El Niño causes drought-like conditions in Australia and southern Polynesia, significantly lowering rainfall levels. Typical cyclone activity is on the rise in several archipelagos, including Tahiti and Hawaii, as a result of El Niño. Warmth surrounds Japan and Korea, resulting in muggy summers and pleasant winters. Southern Asia, which stretches from Indonesia to India, is less fortunate since the rise in temperature is followed by a sharp decline in rainfall, which causes severe droughts that can continue for years. In Africa, the southeastern region of the continent, which is devastated by droughts and higher temperatures, is where El Niño's effects are most notable. However, rainfall in the Horn of Africa increases. The repercussions of El Niño in Europe are still not fully understood. They have a shorter impact and are less harsh. So we have a basic understanding of what El Niño is and how it affects the world. However, the Earth's rotation rate change is arguably one of its most intriguing impacts. This is how it works. Imagine the Earth to be a skater whirling on ice. The skater speeds up their spin by bringing their arms closer to their bodies as they turn. This is due to the requirement of the conservation of angular momentum, that the skater's rate of rotation rises as their arm radius falls. Similar to this, when there is an El Niño, the wind patterns in the Earth's atmosphere alter, which causes the distribution of mass on the planet to change. The total angular momentum is conserved through a reduction in the rate of rotation of the Earth. Even a little change in the Earth's rotation can have significant effects, such as affecting weather patterns and raising or lowering the sea level. This change may appear insignificant. The Earth can thus alter its rate of rotation to take account of variations in the atmosphere, just like a figure skater. We continue to track and research El Niño in order to forecast worldwide weather patterns and comprehend how climate change is affecting our globe. So keep in mind the tale of how the lives of anchovies and people in Peru are strongly related to the El Niño Southern Oscillation the next time you order a pizza with anchovies or open up a tin can with a rollaway lid. The stratospheric polar vortex is a seasonal high-altitude atmospheric structure that develops in October, consolidates in winter, and dissipates in spring. The term has frequently, albeit incorrectly, attracted media attention in recent years. Sudden alterations in tropospheric circulation are frequently caused by its developments and deviations from the vertical axis of polar latitudes. A sudden spread of polar air towards mid-latitudes has been caused by variations, particularly in recent years. We shall learn that polar vortex is a structure that also exists on other worlds. It has historically been crucial in determining Earth's climate history, especially over the last 2.5 million years, which have been marked by a series of recurrent glacial periods and shorter interglacial periods. Due to the vagaries of the polar vortex, we periodically have the good fortune, or bad luck, to experience climate conditions that were typical during the last glacial maximum. We can momentarily travel back to Earth's conditions 20,000 years ago. However, there is a risk that over time, some say within a couple of decades at most, the polar vortex may finally collapse, ushering in a permanent ice age rather than just a few advantageously cold weeks. Possibly, or just highly unlikely. Let's attempt to make sense of this. This inquiry is mostly aimed for people who live in regions with intermediate latitudes, such as the north of the United States or Northern Europe, who have undoubtedly encountered it. On a cool autumn night, you retire to sleep only to wake up feeling quite chilly. An unpleasant surprise occurs when you look outside and see that your automobile is covered in ice and half a meter of snow. One would most likely hurriedly put on the television in a quest to find out what has happened, just in time to hear your favorite meteorologist humorously explain that the reason for your small surprise was the abrupt collapse of something known as the Polar Vortex. Since temperatures dropped to dangerously low levels, in some places nearly 50 degrees below zero, in January 2014, this undoubtedly is when many discovered this for the first time. Even in the tough state of Minnesota, where the weather is generally quite atrocious, the governor decided to close schools to shield children from the cold. But perhaps we don't have to go so far back to see an example. The United States endured an abnormally cold spell in December 2022, with snowstorms and temperatures that resulted in at least 63 fatalities. The same thing occurred in February 2021, when Texas had some of the worst temperatures in over 30 years. As a result, at least 250 people died. In fact, the United States has been experiencing abrupt drops in temperature during the winter months for a number of years, seemingly going against predictions made by proponents of global warming. And yes, as the meteorologist mentioned earlier, these phenomena are connected to the Arctic vortex, the large low-pressure area that hovers over the North Pole. The polar vortex, however, new to us as it seemed at the time, was nothing new to scientists who had been researching it for at least 30 years. So, what is the polar vortex? The polar vortex, often referred to as the Arctic vortex, is a broad area of low pressure that, at high elevations above the North Pole, is semi-permanent. It is substantially larger than any other low-pressure area and is almost always present, especially throughout the winter season. In this situation, we're talking about a vortex that covers the entire Arctic Circle, with the center roughly over the North Pole, which is not exactly little when we take into account the low-pressure regions affecting Central Europe that can have a diameter of 1,000 to 2,000 kilometers or even more. With a circumference much greater than 5,000 kilometers, it can reach mid-latitudes. Typically between 12 and 50 kilometers above the troposphere and tropopause, where the majority of atmospheric processes take place, the stratosphere is where the vortex primarily forms. But when it's strong, this vortex at higher altitudes frequently also impacts the lower layers of the troposphere, resulting in the formation of a tropospheric polar vortex. In meteorology, the tropospheric vortex, which has a greater impact on air masses nearer the ground, is distinguished from the stratospheric one. The stratospheric vortex normally forms around September, achieves its greatest intensity in January and February, and disappears in April to early May. In contrast, the tropospheric vortex is present mostly throughout the year. This circulation can be compared to a huge spinning top that is over the North Pole and is packed with icy air. It resembles a two-story building with a ground floor and a first floor, much like a house. The troposphere in this illustration stands in for the region between sea level and a height of about 10 kilometers, where the meteorological phenomenon that we frequently study takes place. The stratosphere, which is located much higher on the first floor and reaches an altitude of about 50 kilometers, is divided from the troposphere by a ceiling known as the tropopause. Looking at this, one could see an almost circular cyclonic zone with air masses moving counterclockwise and an edge bordered by more or less prominent undulations if we could look down from a position in space above the North Pole. In meteorology, these waves are also referred to as Rossby waves. The Antarctic vortex, which is a comparable vortex that is also found above the South Pole, will be discussed a little later. But what stops this vortex from continuing to move or enlarge? The so-called warmer jet stream, a rapid airflow that acts as a barrier to the Arctic vortex, like the rim of a bowl, typically contains the Arctic vortex above the pole. This bowl of warm air efficiently traps the cold air in the center because it is denser there. It is difficult to go over the rim, or at least, it doesn't do so frequently. When Arctic temperatures rise, a portion of the cold wind vortex may break through the bowl's border, extending beyond the normal range of the jet stream and into continental areas. The terrestrial polar vortex is a frequent characteristic, in particular on all planets with a thick atmosphere, as has been recognized for decades. Where the air density might appear insufficient to produce such occurrences, similar cyclones have been observed near the poles of Venus and even Mars. However, although having a similar origin, a gaseous fluid encircling a celestial planet that rotates, these cyclone shapes and sizes significantly diverge from those of Earth's. The amazing hexagonal vortex that surrounds Saturn's North Pole is one famous example. The interplanetary Voyager 1 spacecraft initially noticed this particular hazy deformation of the planet in 1981, and the Cassini probe did so later in 2006. With better imaging capabilities, what first appeared to be an oddly geometric configuration changed into one of the oddest and most famous wonders of our solar system. A nearly perfect hexagon with sides reaching about 13,840 kilometers, longer than the diameter of the Earth. Traditional explanations are unable to explain how this unusual structure came to be. According to one idea, atmospheric dynamics and Saturn's unusual rotation system are related. This concept, however, begs more questions than it answers. How can a gaseous planet have winds that are remarkably stable and orderly? And why a hexagon rather than any other shape being created by these winds? The impact of air waves is a different theory. The interaction of atmospheric winds and waves in a closed-loop current pattern is theorized to be the cause of it. However, even this idea is complicated and leaves several questions unanswered. However, it's intriguing to observe how the hexagonal pattern might be viewed as a much more geometric form than the wavy border of the Earth's polar vortex. The polar hexagon of Saturn is not an unusual occurrence. Neptune and Jupiter are two other gas giants that have similar structures. This raises the possibility of a general atmospherical mechanism that we, as of yet, are not completely aware of. Even Saturn's South Pole has a sizable vortex in the middle of it. But unlike the North Pole, the Hubble Space Telescope has revealed that the South Pole lacks any distinctive or continuous cloud formation, much less a hexagonal one. Returning to our domestic concerns, the polar vortex may appear to be a somewhat dependable natural system for balancing the climate in either hemisphere. However, in actual use, it isn't quite as seamless. To begin with, the jet streams that define the vortex's perimeter are wavy rather than round, with protrusions or indentations depending on the cold air or warm air flowing according to the latitudes as they approach the pole. The high wind speeds that make up the polar vortex's barrier can also occasionally change in strength. If these winds diminish too much, the vortex may be distorted and its limits may become even more erratic, allowing pockets of chilly air to escape. Even if the air spilling over the bowl's rims is milder than the usual Arctic winds, it is still quite cold. Even with mountain ranges to provide protection, significant snowfalls in Texas and Europe 2 years ago occurred due to this temperature. Speaking of which, why does the Arctic air spilling from the bowl of the vortex wreak havoc in North America but not in Europe per se? Similar latitudes can be found in North America and Europe. New York's latitude is similar to Naples. However, simultaneous cold waves seldom impact both continents, and these winter events are significantly more regular and strong in North America. These differences have a variety of causes. First of all, while the polar vortex can also affect Europe, the air that reaches it travels over the North Atlantic rather than Canada. Due to the warm Gulf Stream, air over land masses is typically colder in winter than air over oceans, especially north of Europe. The key factor making Northern Europe's climate milder than that of Canada and most of North America is this stream. On the other hand, cold ocean currents have an impact on the shores of North America. In contrast, Europe may also rely on the Mediterranean Sea, another heat reservoir, much like the Gulf Stream. Mountains are another factor that makes North America more susceptible to cold air from the north. Northern winds are not blocked by the Rocky Mountains, which run from British Columbia, Canada, to New Mexico, USA, from north to south. Instead, they assist in directing these winds eastward. The main mountain range in Europe, the Alps, runs latitudinally. This prevents cold air from the north from entering and contributes to Italy's temperate climate. The Ural Mountains run longitudinally, separating European Russia from Asian Russia. Despite this, they also help to block cold air, especially the Arctic air from Siberia, which is the nearest significant cold continental area. Siberia is significantly farther away from Europe than northern Canada is from the United States. Therefore, its weather patterns don't always affect those of the continent. Of course, the question everyone is asking, and you might be too at this point, is the polar vortex influenced by climate change? The polar vortices can be distorted by warming temperatures, which can lead to abrupt cold periods, according to proponents of the hypothesis. The reason could be related to the fact that more Arctic sea ice is melting throughout the summer. The Arctic Ocean warms and releases extra heat during the winter as ice melts. The winds that create a barrier between these regions are weakened by the warmth because it somehow lessens the difference between the Arctic air and the atmosphere further south. The polar vortex then becomes weaker and is disrupted as a result. The vortex has a larger tendency to weaken in years when a sizable chunk of the Arctic sea ice is speeding its retreat, according to statistics from the last decade that support this notion. It should be noted that not everyone agrees that variations in Arctic sea ice can have this much of an impact on the polar vortex's stability. But if accurate, that would be worrying because the amount of Arctic sea ice changes from year to year and has been vanishing more and more quickly as of recently. The Atlantic would become more salted, and the well-known conveyor belt mechanism that allows the Gulf Stream to warm Northern Europe and North America would be severely disrupted if Arctic ice continues to melt at an even faster rate. Along with changes in air circulation in the Southern Hemisphere, this might cause a significant deterioration of the climate in the Northern Hemisphere. Additionally, the albedo effect of sunlight reflecting off the white ice might further lower world temperatures if the polar ice caps grow. The Arctic polar vortex may collapse in on itself if this pattern persists. This might set up all the circumstances for a mini ice age to start in the Northern Hemisphere. It's paradoxical because we may have to accept the possibility that global warming could result in a sharp decline in temperature throughout the year. So, my friends, it appears that our planet's environmental destiny is still very much up in the air. The best course of action could be to stay away from anything that could activate climate mechanisms that we still don't fully understand. What's your thoughts on this?